Sure.
So hello, everyone. Welcome once again to our colloquium meeting. Today we have here our guest, Romain Quidant. So I will introduce him. Romain, he received his PhD from the University of Dijon in France. And after that, he went to ICFO in Barcelona. And he was appointed a professor there in 2006 and started leading the plasmon nano-optics group. Romain is a very multidisciplinary researcher, so he works on various topics. His papers often interface fields like nano-optics and nanotechnology and biotechnology, chemistry, and levitated optomechanics and quantum optics. So today he will talk to us about nanophotonics. I asked him to talk about that because that's a bit of his research side also, which I'm less familiar with because I'm working on optomechanics and he also works on that. So there's this point of contact. And okay, maybe I should say for those of you who know, so now our former student Bruno Mello, I think he's here watching the talk. He's doing a PhD with Romain in ETH. Romain started his group at ETH-Zürich recently, and Bruno is his PhD student there. So yeah, we know Romain now through Bruno. So Romain, thank you very much for accepting to give this presentation. Welcome to the colloquium. I'm looking forward to hear you. Thanks.
Thank you so much for the introduction and for the kind invitation. So that is a pleasure for me to be here to tell you a bit about what we do in the field of nanophotonics. And I would say with this talk today, I have two objectives. So the first one is to introduce nanophotonics to the newcomers, and the second one is to highlight somehow its interdisciplinarity. So what I've done is to select a range of quite diverse topics where I'll try to illustrate, as stated in my title, that nanophotonics can be used as an enabling technology, both in basic research, but also in technology. So let me see, yeah. So nano-optics, nanophotonics, you will hear both terminology, is the field that study the interaction of light with tiny pieces of matter down to the nanometer scale. And the main, let's say, motivation behind this is that when matter is scaled down to this nano size, it starts to feature some optical properties that do not exist at a larger size. Okay, so what is so special about nano-optics or nanophotonics? And to start answering this question, I would like you to imagine a model experiment, very simple one, where you have light impinging on an aperture in an opaque screen. And we will consider that this incident light is a plane wave. And so if I use some very simple Fourier consideration, what will happen if I decrease the size of the aperture while maintaining the wavelength of the incident light? What will happen is that on the other side of the screen, the scattered light and the range of K vector, let's say, will increase. And by decreasing and decreasing the size of the aperture, this range of K vector will become wider and wider. And we're going to reach the situation where the size of the aperture is going to be significantly smaller than the wavelength. And for this situation, the range of K vector on the other side of the screen will be so broad that a few of this K vector will be associated to non-propagating wave, so evanescent wave that will be somehow bound to the aperture. And so this means the direct consequence of that is that in the vicinity of this aperture, what we call the optical near field, we will not be subject anymore to diffraction limit. And that would be possible in this region to actually concentrate the light well beyond, let's say, a fraction of the wavelength. So this is the first, let's say, feature of nano-optics. Another feature, another asset in nano-optics is the possibility to design a variety of nano-optical resonators that are going to be essential in engineering the light-matter interaction on the nanometer scale. And so if we want, let's say, an overview of these nano-optical resonators, I would classify them in two families. The first family is about nanoresonators that support geometrical optical resonance. And so here, this is completely an analogy with what would happen with a microscopic cavity, where the resonances of the resonator would be defined by the ratio between the dimension of the cavity and the effective wavelengths within the cavity. So what happens here at the microscale would happen as well at the nanoscale. In this, for instance, in this nanoparticle, that would be typically, a dielectric with a high refractive index or a semiconductor. So I would like to show you, for instance, an example of this geometrical resonance in an optical resonator. And this is illustrated here with this silicon nanoresonator. This is a cylinder of about 300 nanometer diameter that is lying on the substrate. And what you see here is the near field distribution of a high order mode of this resonator, where you can see nicely how the field is structured in very tiny region inside and also at the near vicinity of the resonator. So these are, let's say, more intuitive ones. These are the equivalent, as I said before, of, let's say, cavity resonances. And there are other kinds of resonances that are very interesting in nano-optics, like the ones that are associated to the material, like surface plasmon resonances. So in the case of surface plasmons, and that would be more in the case of metals or highly doped semiconductors. So the electron cloud of the metal would be driven by the incident electromagnetic field. And typically for a particle that will be very tiny, spherical, this resonance would happen when the real part of the electric permittivity is negative and equal to twice the dielectric permittivity of the environment. And so what I'm illustrating here at the bottom are simulations that show the electric field intensity, actually the normalized electric field intensity nearby different gold nanoparticles. If you look at something like, let's say the simulation on the left, where you can see a 50 nanometer diameter gold nanoparticle at resonance, at the plasmon resonance, you can see that even more than these dielectric resonators that I was showing before, there is here capability to really concentrate the light very strongly at the surface of the metal. And what is nice about plasmonics is that when I start playing with the geometry of the particle, but also when I start using collective effect between adjacent particle, like in this right simulation, I will be able to gain even further control over the near field. And for instance, if you look at the enhancement factor here of the intensity, for instance, if you compare what happened with a single particle and what is obtained in this case in between these two antennas, you can really obtain like a very strong field concentration and a capability, of course, to strongly interact with any matter that would be exposed in this region. So whatever the nature of the resonator, so whether this is a geometrical resonance or whether this is a material resonance, eventually, this means that at resonance, you're going to observe a peak in the extinction of the nanoresonator. So I will be able, by changing the structural parameter of the resonator, geometry, material, etc., environment, I will be able to tune this resonance all over the visible spectrum. So I said a peak in the extinction. So extinction is the sum of scattering and absorption. So that means that both quantity are going to be enhanced at resonance. So I would like we have a look a bit separately to each of them. So first, scattering. And so what people have learned over the years is that these nano-optical resonators, they enable, as I've just illustrated, to concentrate the light at sub-wavelength scale to achieve a very strong enhancement of the field intensity locally. And so that means they're going to be able to interact with matter in a more efficient way. And because they are resonators, like any kind of resonators, when you start modifying the environment, you're going to have basically a modification of the resonance. So there's going to be possibility to use them as a very efficient sensor. And another thing that people learned, I would say maybe the hard way, is that these are typically very lossy resonators. So especially if you work in quantum optics, especially if you're used to very high finesse cavities. So these are very broad resonances that are very lossy. And so the way I say it, this may sound like very negative, but actually this is an opportunity to use these lossy nanoresonators as a source of heat that would be remotely controlled with light. So you may wonder why this is interesting. Well, actually this is interesting because unlike what would happen with a large heater, like typical a resistor or something that is macroscopic, I would have here the ability to first to convert the light into heat, but also because the particle is very tiny, to achieve very strong gradient of temperature that would be very difficult to achieve, let's say with a macroscopic, let's say heater. And also because the system is very tiny, the dynamics of the heat up and the cool down are going to be much faster, very, very fast. So altogether, what I'll try to illustrate today is that these specificities of these nano-optical systems, what we try to do in the group is to use them as an enabling technology, as tools to address some problems, so in science and also in technology. And so I've selected these three very different topics. So one is related to on-a-chip sensing, the other one about reconfigurable planar optics. And then I'll talk in the last part about the possibility to use the photothermal effects for a new generation of a new kind of applications. So let me start with the first topic. And of course, when you are in the middle of a pandemic, there's here no need to insist too much on the motivation of having integrated devices that are capable to measure in a fast and cheap way biomarkers in a given sample. So of course, the pandemic is not the only motivation for having these sensors. And in fact, many years ago, people already thought about the possibility of having this device for two main applications. The first one is what I would call screening of high-risk populations. So that means that you would like to test maybe in your doctor's, let's say, room directly during the visit, using just a drop of blood, a given biomarker, and to give the doctor an indication on whether you should be sent to the hospital to do like more exhaustive and more expensive tests. And another application is what is called treatment monitoring. And so that means that basically when the patient is already diagnosed a disease and receive a treatment for that, what you would like is these devices to help monitoring regularly the effect of the treatment toward a more personalized medicine. So this said, to achieve that, what we do, and many other people worldwide are doing that, is to follow this concept of lab on a chip. And I like very much this illustration because I think it captures very well what it is. So on a piece of a few square centimeters, what you're gonna have is the integration of one functionality or several functionalities for a conventional analytical lab, and these things will be somehow projected on a small piece of device. So you can have like a different reason for doing that. So they're going to be less invasive because a priori you could do a measurement from a single drop of blood. That may be cheaper. That can be, of course, transportable and faster. And there are many different reasons for doing this. So how does that work? So the first thing you do in order to build such a device, and in our case based on nano-optical resonators, is to create a transducer. So the transducer are going to give an information about the presence of the biomarker you want to detect. And so of course, we're going to use the nano-optical resonators for that. And so the idea is that the resonator is going to be functionalized with a given molecule capable to recognize the molecule one detects. So we have heard a lot about antibodies lately. So this is typically what you would use here, an antibody against the molecule you want to detect. If, for instance, you want to detect a protein. So you would send light on this, you would measure the extinction spectrum. And then of course, if you expose this sensor to the blood sample or the saliva or whatever, you're going to have, if the analyte is present in the sample, you're going to bind specifically to the antibody. They're going to modify the environment of the sensor. And this, of course, going to lead to a shift of the resonance. And this is precisely by monitoring the change in the peak position over time that we're going to be able to get the information about the actual amount of molecule that is present within the sample. And so typically, if you would monitor this germ here, they're going to be directly related to the concentration of the analyte. The second thing you need to do, second ingredient to build such a lab on a chip is, I would say, to keep the analogy with the nice illustration I was showing at the beginning, is that if the nanoparticle is the machinery, what you need is to have the lab environment. So to have the rooms and the corridors that are necessary for this machinery to operate in a very controlled environment. And for that, what we're going to do is to use microfluidics. So microfluidics is the technology that is used to control fluids, as you know, on very tiny scales. So what I'm showing here is a chip that is actually made of PDMS, of 2 layers of PDMS. The blue layer is the sensing layer, so where we're going to have the nanoresonators. So this is what is in yellow here. So these are arrays of nanoparticles, as you see here. In that case, they are metallic nanoparticles. And on top of that, there is another layer that is the orange layer, and this is what is called the control layer. And so to understand how it works, you see that the control layer somehow at certain location, it overlaps with the flow layer. And so what happens is, because PDMS is a flexible polymer, when you're going to inject some liquid or some air in the top layer, this will collapse the underneath channels, and they're going to operate like a valve. And eventually you're going to be able to do like very sophisticated operation, as I'm going to show in a minute. This is how it looks when this is assembled. So of course, I need to change here. It's not anymore a euro, I should put here, this is 1 franc. And what you have at the center is the, let's say, sensing region. All these holes here are the interface with the outside world. So this is where the sample will get in and also where you get out. This is also what we use for the control of the valves. And the sensors are located somewhere there. So what I'm showing here is actually the same chip I was showing that is operating. So of course, here we put some nice dyes in the chip to make it more visual. But what you're going to see is actual sequence that is used in this chip to detect at the same time 4 different cancer biomarkers directly in human blood. And so this change of colors you're going to see is basically the automated operation of the chip. So there's a computer that is controlling these valves. And all the sequences you see are including the incubation, the rinsing, all the different steps, the amplification. So all together, there's no need for pipetting or whatever. Everything is done automatically. So for whoever may be attending the talk that is doing manual pipetting, you will understand what this means. This is a true advantage. So eventually, as I was saying, this chip was used to recover some cancer biomarkers in blood. And so these are these markers here. And basically, just to make this long story short, we were able to retrieve on a blind experiment the concentration of the different markers with an accuracy of about 25%. So it doesn't sound like super accurate. It's actually not so bad. And of course, there's here quite some room for improvement. What I was showing here is related to plasmonic sensors, so gold nanosensors supporting surface plasmon resonances or localized plasmon resonances. And so over the years, there have been quite some work on the use what is called high refractive index nanophotonics. So what does that mean? So here we, instead of using material resonances, so plasmon resonances, we're going to use geometrical resonances in either high refractive index dielectric or semiconductors. So we're going to use the fact that the effective wavelengths within this, this material is very tiny. And you have, I'm sure you know these resonances in the form maybe of Mir resonances or things like that. So this is a bit what is happening here. So why would you like to use that, for instance, in sensing? Is because the loss is going to be reduced, but still you're going to keep a strong confinement of the modes. And there is something you're going to understand in a moment. Normally in plasmonic nanoparticles, you would not have a strong magnetic resonance just because of the field that cannot penetrate into the metal or not deep into the metal. And so this is not the case in these dielectrics, and this somehow provides some new opportunities in the engineering of the modes. And I'll explain that in a second. So the first thing we were doing is actually just reproducing what I was showing you before, but with this time not anymore gold nanoparticle, but silicon on quartz. And so these are cylinders that are slightly bigger than the plasmonic nanoparticles, but they show resonance like typically in the same region, somewhere in the near infrared. So the chip is very similar. And so what we're doing is to choose one marker. And the first thing we did is to compare the performance of these two different resonators to see whether these guys actually would be competitive with plasmonics. So what we found, and this is again summarized a lot, but this is just to give you a flavor. We found out that these are the performance. So the way you should read here is the response of the sensor, so the change of resonance as a function of the concentration in the log scale of the PSA, so this prostate cancer biomarker. And so the take-home message here is that basically this is performing more or less the same as plasmonics. Some advantages, some pros, some cons. So you can say, okay, so this may be not so exciting. The reason why this dielectric resonators is actually exciting is more, let's say, beyond the detection of a given concentration of biomarkers, is to detect chiral molecules. So I'm sure you know, chirality is an essential feature in nature. In particular, maybe many of the building blocks of nature are actually chiral. And so what is critical is that these guys, so these chiral molecules, their biochemical properties strongly depends on the handiness of the molecule. And I'm sure you heard about terrible stories about drugs that would have the wrong enantiomer and would generate a lot of issues just because, of course, the bioactivity would be very different. So normally, two enantiomers, so two molecules that are symmetric from each other in a mirror plane, they are very similar to each other. And the way to discriminate between them is usually to make them interact with another chiral object, okay? And so what people have been doing for many years, as you know, is to, for instance, use as a chiral object, chiral light. So if you do a typical CD experiment, so circular prism experiment, you would have a cuvette with a high concentration of the molecule you want to characterize. You would send left circular polarized and right circular polarized, and you would do a differential measurement in transmission. And this would give you this kind of curve that would show a symmetrical response depending on the enantiomer. And look at the wavelength range. So we are here around 200 nanometers. This is where the molecule actually absorbs. So this is typically where you would find these CD features. Issues of circular prism, let's say conventional ones, is that I'm sure if some of you use them, so there's usually like big machines. This is a very tiny signal. This is in the UV. So there are many issues here. And so usually you need a high concentration of material to measure it. So the question I would like to raise here is whether nano-optics and these nano-optical resonators could be useful for the detection of these molecules. And so to answer this question, I would like we take a step back and we understand a bit how whole light or chiral light interactive chiral molecules. So let's consider a chiral molecule that is, let's say, characterized by what is called the Pasteur parameter, and this is this kappa, is a complex quantity. They're going to be illuminated by a chiral light, and the way to quantify the chirality of the light is what is called the density of optical chirality, that is C. And eventually, what you can show is that the differential absorption I was mentioning before, when you do a chiral measurement, a CD measurement, can be expressed very simply, or at least proportional, as the product of the chirality of the molecule and the chirality of the incident light. So it's pretty cool and pretty powerful. Of course, the chirality of the molecule, you don't have control on it because it's a natural molecule, but you do have control on the density of optical chirality. If you consider, this is the expression of the density of optical chirality, this is C, and that depends, as you can see, on the imaginary part of E star H. And so if I'm using a plane wave, circularly polarized, this is the expression I'm gonna get for C. So eventually this will depend on the intensity of the light. And so since my nano-optical resonators, they are actually able to enhance the electrical intensity, maybe I have a way then to enhance delta A. This is the quantity I want to enhance. So indeed, so people have been thinking about that for years now. And the only small detail is that if I want to involve an optical resonator, I need to take care of something. So for instance, if I use an elongated gold bar, like in this case, so this is the intensity in the near field, and this is the C locally, so this is distribution of the C. So of course, because this object is non-chiral, if I integrate the C all over the space here, all over the mode space, what I'm going to get is 0. Okay, they're going to give you locally. I'm going to have strong values of C, but all together integrated, they're going to be 0. So I need to redefine delta A with an integral. That's going to be the difference between C plus minus C minus, and this will be integrated over the whole volume. So I need to make these things non-zero and to maximize it in order to maximize delta A. So I have a way with nanoptics to do that, but the question is with what kind of system? So people have been doing that already beginning of the year 2000. So in particular, the group of Jaludev was very active in this topic, and the idea was to design plasmonic nanoparticle that would have this chiral shape, so helices or any kind of system like that. They were showing that it was possible to achieve a superchiral field with the structures. And then more recently, it's already a while ago, in 2010, people were showing that this kind of structure could be used to enhance chirality. So I'm coming back, all that was with plasmonics. So I'd like to come back to this silicon nanoresonators I was mentioning before. And basically here you have two advantages. So the first one is that, as I mentioned before, these guys, they have a strong magnetic resonance, not only a strong electric resonance. And the good point is that by changing the diameter of the cylinders, we're going to be able to detune the electric and the magnetic dipoles. So I'm going to play with C. I'm going to be able to adjust and to engineer C. The second thing is that unlike the plasmonic structures I was showing before, where C has the different signs all across the structure, these cylindrical silicon resonators, the ability to really preserve the endiness of the field, the polarization. So eventually, when I'm going to calculate the integral I was showing you, I'm going to have a maximized CD response. Okay. So how do we do that in the? I'm just making sure I'm not talking too much. Thiago, you need to stop me whenever you feel that I'm getting over the time. Okay.
Oh, we are about halfway gone.
Okay.
Now you have time.
Okay. So in the experiment, what we do is to have these silicon nanoresonators that are fabricated on the quartz sample, as I mentioned before. And so in this experiment, we will evaporate on top a chiral molecule. This is this filling aniline that has, let's say, a thickness typically 100 nanometers. And so the whole point is that by probing the system in different regions, I'm going to be able to somehow isolate the contribution of the silicon resonators in this role to boost the CD measurement. So first, if I do the measurement in this region where there's no resonator, what I will measure is exactly what I showed you before in the first slides. So it's a typical CD measurement, despite the fact that this is a film instead of a solution. And what you see is that there is in the UV region, there is a deep. For the D molecule, there is a maximum, sorry, the other way around. For the other enantiomer, and for the racemic, there is a flat response. But I insist this happens in the UV where the molecule absorbs. So now let us measure in this region. So where I have the molecules that are coupled with the resonator, and I have detuned properly my electric and magnetic dipole in order to maximize the density of optical chirality. And eventually what I observe here is a very similar response. The only difference is that now this happens in this region of the spectrum. So we are here at the resonance of the resonators. And so I see this nice symmetrical response. And I see also, I check that the response for the racemic is actually symmetrical. So how do I interpret that? Our interpretation of the system, and I must say that it's still open interpretations because people do not really agree on how this thing is happening, is that somehow the molecule transfer its chirality to the nanoresonators. And what you see in this near-infrared region is actually the feature of the hybrid system that has become chiral because of this transfer. Okay. Also, another thing you should notice is the vertical axis. So here is in milli-degrees, and so you can see that actually the response in near infrared is not only appearing, it is also significantly stronger than what would happen in the UV. So this is what we believe very exciting area, and we keep let's say pushing this line of research. So I would like to come now to something that is quite different, and that is for maybe those of you that are more interested in maybe in microscopy and imaging, also in integrated, let's say, optical elements. And here the motivation is this concept of flat optics that has been kind of boosted more recently. And a way to summarize that is just to say that I think this is just captured on this picture, is that you would like to integrate in a quasi-2D system optical functionalities that are normally provided by a bulk optical element, like for instance, this subjective lens here. And so the reason why you would like to do that is first because these guys, they're full of, of lenses, and you would like to be very thin. You have now, as you know, a lot of effort in the virtual and assisted reality, and more, let's say, exotic project, maybe long-term project. More than exotic is people are even thinking about artificial vision. So normally the way people do that is not the only way, but one way that has been very exciting this last decade is to use the concept of metalenses. So metalens is an artificial engineering of the refractive index. So this is done at the subwavelength scale. And what you're going to do is to take your region of interest, you're going to pixelize it with some tiny resonators like these guys. And each of the resonators will engineer the phase of the light that's going to go through the metalens, okay? So by changing the orientation, by changing the dimension, I'm going to be able to control all the phase between 0 and 2 pi, and eventually to map a phase front that is basically what is needed to achieve the optical functionality I want to achieve. In particular, if I want to do a lens, I'm going to shape all these elements in order to reconstitute the same, let's say, phase accumulated when you go through just a bulky glass lens. So normally, so there are people that have been extremely successful actually. Now there are even companies that distribute these things, and the features are actually very similar to what an objective, at least in terms of numerical aperture, can do. But then, of course, when you think about the application we were mentioning before, what you would like to do is not only to be able to have a fixed optical element, but to achieve some reconfigurability. And so there people are pushing different directions. They are using like carrier injection. They are combining them with phase change materials, or they're even using some MEMS technology, for instance, as illustrated here. So what we've been doing over the last year is something a bit different, is to use a very simple physical effect, the thermo-optical effect. And so basically we use the fact that most electric materials have the refractive index that changes with the temperature. And as you know, this is what is behind basically the Mirage Effect. So I'd like to explain how this came to our mind, because it is kind of I think a nice story. So that was during the PhD of John Donner, already some time ago. And John was studying some arrays of plasmonic structures that were some kind of immersed into this fluidic chamber. So there is water here. And he was shining light in order to couple to these resonances, the resonances of this particle. And he had that in the microscope. And what he was seeing is that as he was cranking up the power coupled to the resonators, he was seeing a shift in the focus of the microscope. And so that was kind of strange observation. And then we realized that there was actually a change of the refractive index in the water that was induced by the heating of this nanoparticle. And he did that in a more controlled way, and was able to show that by increasing the power, the focus of the objective was shifted in a very controlled way. So what we did with time is to drop somehow the plasmonics and to go toward a more electrical implementation. And so the equivalent, electrical equivalent is what you see here. You have this somehow pixel. So this is a resistor made of gold in that case, that is on a glass substrate. And what we use as a thermo-optical material instead of water is a polymer. This is actually PDMS. So we have a thin layer. And so the idea, again, is that by the Joule dissipation within the resistor, I can increase the temperature nearby. This will change the temperature within my polymer. And this will be translated into a refractive index change. So if I'm able to shape my temperature landscape, I may be able to achieve some functionalities, like, for instance, a lens. So the first thing we did related to these metal lenses I was mentioning is to combine that with a fixed silicon metal lens. So this is, I think, well sketched here. So you have this fixed metal lens, and what we do is to cascade this thermo-optical module I've just described. And so, so let me go maybe a bit fast here. The idea is that we have the fixed metal lens. These are the features. And this is the experimental. So basically the lens is like this, and we see the transversal focus of the lens, okay? And then we combine that with this thermo-optical module that I can just skip that. And what we observe is that by increasing the dissipation of energy within the resonator, in that case by increasing the voltage we apply, we are able to shift the focus by a certain amount, a significant amount, just by increasing the voltage from 0 to 9 volts. And of course, I can achieve with a quite reasonable accuracy all the position that are intermediate here. So all that is kind of intuitive, because in fact, I must say that, this design I was showing is completely intuitive. So the idea is to get something that was kind of a Gaussian-like profile of refractive index, but this is not something that is really engineered. So the next step was the following, was to say, is there a possibility if I want to go beyond the lens, or even if I want to do a lens, but I want this lens to be like really performant, is there a way to start from the desired wavefront and to basically solve the inverse problem in order to find what is the optimum design for the resistor. And so here, there has been a major contribution from Pascal Berthaud, that was postdoc in the group a long time ago, but then is now an assistant professor in France. And so what he did is to consider the system would be formed by different rings, and these rings would have different diameter, of course, but they would have also different width. And so by playing with the widths, that's a way also to play with the resistance of these wires. And eventually, as I said before, we're going to start from a desired wavefront, and using a genetic algorithm, we're going to find out what is the optimum design. So what I'm showing here is kind of a reconstitution of what Pascal did. And so you see that we aim at a conical wavefront. And through these different iterations, I think we're going to get to 50 or 60. We're going to eventually find out what is the optimum design for the resistor. So here we go. So we have, let's say the closest things closest to the ideal wavefront we aim at. And so of course, if you apply that, you can do like all kind of things. You can do, for instance, an aberration-free lens. You can do a plateau of phase. You can do this conical thing I was mentioning. And you can start even to break the symmetry, this angular symmetry, because if I'm able to play with the width of the resistor, I'm going to be able to really have all kind of control over the resistance. So what you see here, all these data are actually experimental data of the temperature and of the actual wavefront of the light going through the system. So when we talk about heat, usually we think, okay, fine, but this is very slow. It's very slow because we have this experience of, kitchen of the pan, and you heat up, and these things takes a while to reach an homogeneous temperature. But in fact, there is a rule of thumb that tells you that the time it takes to heat up, is determined by the square of the size of the system divided by 4 times this AS is what is called the thermal diffusivity. So the important things, of course, here is that this is the square of the size. So if my system is small enough, I will be able to really reach response time that are quite reasonable. And so in particular, if I have a system that is below 100 micron size, I start to be below 100 milliseconds. This starts to be very relevant for vision and for imaging. One of the last thing I wanted to show you here is on this topic is basically that by having an array of these pixels and being able to operate each of these pixels separately, we can do like multiplane imaging. So what you have here is a super simple experiment, because you have basically this smart lens that is coupled to an offset lens here. There's a camera. And what we do is to image, or we'll try to image in the camera plane, these different pillars that have these RGB logos and that are positioned at different planes. And so the video I'm going to show now is how we individually adjust the voltage in order to put in focus each of the posts. And in fact, there's an algorithm that kind of identify when the focus is kind of obtained. Eventually, of course, if I switch off, the thing's just coming back to the original. And so the reason why I'm sure you guessed, the reason why we were using this RGB is basically we were interested in the chromaticity of the operation. Because what you don't want, if you want to use that for imaging, for instance, as we said, for a mobile phone and camera, you don't want the system to be chromatic. And the good point is that since it's not a diffractive element, this is something that is based on the property of this PDMS. This is actually a very flat response. So this just measured from 400 to 650, but actually no change if you push it to the end of the visible. So this is a quite flat response. Tiago, how am I doing with time?
So you have about 15 minutes more.
Oh, yeah. No, I'll just take 10 because I don't want to saturate people neither.
Okay.
I just talk about two applications that are related again to heat. And here we're gonna, again, come back to this plasmonics. And so the first thing we're very interested in is to see whether the thermoplasmonics, so the generation of heat, so the conversion of light to heat with plasmonic nanoparticle could be used for additive manufacturing. And you know, 3D printing is everywhere, is used in many different circumstances nowadays. So for prototyping in the automotive industries, widely used, and even actually we may not know, but our glasses or most of the time, or more and more at least, are done by 3D printing. So not only the frame, the actual lenses, everything is done by 3D printing. And so there are many techniques, as you know, 3D printing. And maybe if you want to kind of benchmark them and quantify the performance, you may define, let's say, these three main criteria. So the robustness, of course, of the print. You want the print to be fast. You don't want to wait for ages for having your piece. Another one that seems like very superficial, but is a true issue, is the aesthetic. So you want to be able also to control the color. And so somehow it turns out to be very difficult to be in this sweet spot where you would actually meet the three parameter or the three criteria at the same time. There's a technique that is called HSS that I'm going to explain in a moment. It's actually doing pretty good because it's fulfilling these two aspects here, but unfortunately there's no control on the aesthetics. And so the idea is whether we can actually move these things nearby here. So what is HSS? That stands for high-speed sintering, and the idea is actually a very clever idea where you would have like a bed of polymer beads that would be somehow compacted on the bottom of your sample, and you would apply, maybe with inject some ink at a very specific region, and this ink would be an absorbent ink. And the idea is that then you would radiate, you would illuminate, and where the ink is located will be absorption, temperature will rise, and therefore the adjacent beads will actually sinter, they would fuse somehow. And so of course you would do that, you would do that one layer, and then you would do a second layer. And this is very fast because you don't need to scan anything. You just need to inkjet and then to put the light, white field. And so that can be very fast, very robust as well. The only issue is that most of the print have this color that you see here, like a dark gray or black. And so the idea here, I'm sure you already guessed, is to use, instead of this carbon-based ink, to use plasmonic nanoparticles. So this is a solution of gold nanorods that have been engineered to be resonant just at the edge of the visible. And so the idea is that with this invisible ink, to be able to overcome the limitation of the carbon-based ink. So I go fast, but the idea is summarized here, is that this is what you achieve with carbon black, and this is what you achieve with this invisible solution, invisible ink. And this is not only that you get this more white color, but this is also that you can actually, you need less energy for a given concentration of material, less energy to be able to sinter the polymer. And of course, so if you can do white or whitish, what you can do then is to add some dyes and then to try to reproduce a Gaudi dragon, which is far from reality, but this is for us still very exciting with these three colors already, a very exciting achievement for us. The other and the very last thing I would like to mention, and this is using this heating with nanoparticle for a very concrete application. This is a collaboration we had with the company B. Brown. And Brown is a company that is expert in some surgical parts. And one of their star product is this polymer mesh. And so this polymer mesh is used for hernia repairing, so abdominal repairing in general. And actually, usually when I'm in an audience, I usually ask the question whether there are people in the room that have one of those, and there's always at least one person. So this is a very frequent operation, 20 million operations each year. So this is really huge. What is the problem? The problem is from time to time, too often, of course, some infection can happen during the surgery. And this means that the biofilm will form, and the only way to solve that would be to actually reopen and to change, to clean and to change the mesh. So this is a disaster for everybody, of course. And so Braun approached us to see whether there would be a way to solve this issue. And the issue is the problem is let's say the solution we have here is kind of simple. The idea is that you would take one of these polymer mesh, you would functionalize it properly in a way to ensure very strongly there's good nanorods at the surface. And the idea is that ideally you would treat from the outside with light the system in a way to prevent the formation of the biofilm, also to kill the bacteria in order for them not to develop into a biofilm. So what you see here is a zoom on like a small portion of the mesh. And this is what this two photoluminescence from the gold that enables us to see that basically even at a scale that is start to be macroscopic, we have a rather homogeneous distribution of the nanorods. So there's a high density of them. And this is what this green color is actually telling you. And then this is the film Braun was interested in because this is the one that is generating quite some issues in practice. And the idea, and what I'm going to show is only an in vitro experiment, it's not in vivo yet. We were somehow contaminating the mesh that were previously functionalized with some GONA particles, and we were here testing different kind of illumination. So either a high peak power during a short time, or something that would be milder but during a longer time. And so, so these for given influences, and so these different colors and these figures you see here. So these are the logarithm in the reduction of a number of bacteria. So red is not good, orange is not sufficient, and above 2 logarithm is what is considered relevant for them. And so what you see, at least in this specific set of experiment, is that you rather go for this highly, let's say, intense and short illumination. This is what you're going to get for 40 influence. You're gonna get it's a better result. So the status right now is that Braun is doing some animal tests in order to see whether this can be implemented in vivo. There are many challenges we can discuss if you want to ask that during the Q&A. But yeah, this is where we are right now. And so, of course, today I'm not talking about the topic Thiago was mentioning, is also interested in. So this is levitation optomechanics. So that would be for another time. We have like a significant portion of the group is actually working, and as Thiago was mentioning, so there's a PUC-Rio alumni. So this is Bruno, and so yeah, we're very happy to have him in the group. He's doing a great job, I must say that, and he's actually more specifically working on let's say levitation system for inertial sensing, some integrated version of it. It's fully in his way to get some very nice results. And actually we got through recently with this gentleman you see here, you may recognize some of them. We got a very, what is important here, what is called a NEOC synergy project. And so we're gonna join effort between the four of us to push, let's say, levitation optomechanics toward, let's say here, like more quantum physics application. This is a bit far away from the applications. that's it. This is where we are right now. So this is the main building of ETH. We're just located here on the side. And yeah, that's it. I thank you for your attention, and can take any question you may have. Thank you.
Well, thank you very much, Romain, for the excellent talk. It's very nice. So now we open for questions from the audience. So is anybody out there wants to make a first question? So if
the first one is the hardest.
Yeah, it's starting is the hard. If you want to make a question, please just raise your hands, and then you may start speaking. So okay, if nobody wants to make a question, then I will start. So very nice, Romain. I liked very much. So a lot of new stuff for me, because you spoke about the nanophotonics field. So at the beginning, you were mentioning the nanoresonators that you can use to sense concentrations of molecules by looking at the spectrum, right? So last semester, I teach this biophysics course, and I learned that in living animals, in cells, you know, there are like mechanisms that can sense like single molecules. So even if a single molecule steps in, the thing is still able to produce a microscopic signal. So could you, in principle, achieve like similar resolutions with your nanoresonators, and what limits the resolution? I don't know if you could speak about that a little bit.
Yeah, this is a very good question. So actually, there are some rather recent implementation of single molecular, let's say, binding events that are detected with these resonators. And so here somehow I would say the challenges are the following. So I've mentioned before that these are very lossy resonators. So that means the optical quality factor is actually quite small. And actually, if I said a figure, you serve people from, let's say, alcohol physics would laugh at me, because it's typically a few, yeah, this is 10, basically. 10 would be the quality factor. And so of course, this will affect the sensitivity with which you're going to be able to monitor a very tiny change. Of course, if your resonance is super sharp. But there is another, of course, another parameter that is important. This is how concentrated is the mode. So somehow, when you measure perturbation like that, and this is the same in optomechanics, as you know, the amount of perturbation you're going to be able to measure is related to the, for instance, in that specific case, to the size of the molecule with respect to the size of the mode of the sensing mode. And so these plasmonic nanoparticles are very bad in terms of quality factor, but they are very good in terms of mode concentration. So under specific circumstances, you're going to be able to achieve that. The only thing is that you may need a full optical table in order to measure it. So you need to really, you can imagine, you need really to push the measurement to the very extreme. And eventually in practice, it is not always the most important parameter. For Corona, we see, for COVID, we see that basically what you want is robustness, is time, is you want, of course, to meet the level of sensitivity, but there are some other parameters. But this is super relevant. Yeah.
I see.
Question 2.
Nice. So more questions, guys? Now that I started, does anybody want?
I have one question, Thiago.
Oh yeah, sure. Tommaso, please.
First thing, thank you for your very interesting and complex talk. And
thank you.
I was thinking about the detector of the chiral molecules that you are showing, how to divide the chiral fields using the metamaterials or plasmonic in general. And I was thinking if you ever thought about also, or if you are working maybe on the possibility to make optical tweezer that can separate chiral molecules somehow.
This is as well an excellent question. So this is something that is very interesting. Many groups that I know that is actually trying to push this direction, and that has some challenges. So maybe for those that are not experts, I can maybe develop a bit Tommaso's question. the idea is to see whether that would be possible to have optical forces that would be different for one enantiomer and the other in order to be able to separate these two enantiomers. And that would have practical, very interesting applications, of course, just imagine the pharmaceutical industry. So the challenge usually is that, so these forces, of course, they exist. The problem is that how do they compare to other sources of noise? And typically, if you're working in solution, typically at room temperature, so Brownian motion of these molecules, that would be huge. And so somehow this difficulty people are observing right now is how do you somehow generate an interaction of the chiral light with the chiral molecule that is big enough to overcome basically this Brownian noise. And this is, as far as I know, the main challenge people are experiencing right now. So
you would like the force to confine one chirality, but not confine the other, for example, something like that.
Yeah. For instance, you would like to push one enantiomer here and the other one there. But
like a Stern-Gerlach experiment. You just
completely that.
I see.
Yeah. So, but this is a really cool problem. I mean, so what I try to say is that, the solution is not simple.
Do you think there is a solution?
So what is clear, for instance, is that people have been using artificial, so for instance, they've been using chiral nanoparticles, and they've been showing that that was possible to achieve this, this separation. But of course, because they are already in the range of a few tens of nanometers, the strength of the force is actually big enough to overcome Brownian dynamics. So this is, I think there are good indications that could happen, but the problem is really what happens when you get to the nanoscale, and then the forces are very tiny. Yeah.
Thank you.
Thanks, Tommaso. That's I didn't think about that question, even though I'm working on optical tweezers. That's a good, that's a great question. So anyone more questions? Okay, so Romain, you were mentioning at some point that so the molecule somehow transforms the chirality to the nanoresonator. I didn't understand it very well. Could you maybe elaborate a bit?
So maybe this is because we don't understand it very well. That's the reason why my explanation may not be so clear. So the way you can understand that is, as I mentioned before, the absorption. So to see a significant CD signal, you need significant absorption. So that's the reason why we see, in the case of a pure, you can still see my slide, right? Yeah, you can see my. So in that's the reason why, let's say in a conventional CD experiment, you're going to see this deep and this peak in the UV region. So somewhat what I was trying to say is that the combination of the very, very, very tiny chirality, because basically there is a tail here, and these tails go all the way to 700, 800, okay? The combination of that with the very strong absorption of the nanoresonator, so somehow you can see that as the chiral current of the molecule to still exist, although super, super tiny, but to somehow, because it is coupled to the resonator, you generate kind of an hybrid that absorb a lot. Let's say the resonator provide the absorption, the molecule provide the chirality, to say it, maybe. But again, this is still open to discussion.
I see. It's most likely, but it's still a debate whether it's, you can still.
So some other people would say that it's not that poetic interpretation, that is more that there is this tail of CD that is, and so you have very tiny, and just basically you have an enhancement somehow of the field, and so what you see is a bit is an enhancement of this state. So, but yeah, people are still debating on that actually.
I see. And I have one more question. Maybe I open again if somebody decides to make a question, because otherwise I'll just keep asking it. So I wanted to ask about your, you mentioned the reconfigurable meta lens. Can you use it as a sort of spatial light modulator? I mean, could I change the transverse mode and make these Laguerre-Gauss angular momentum states? Could I think about it in this?
So, yeah, so that would be, that's another very good one. So the idea would be to have, sorry, let me come back here to the, so maybe
I love this video.
Image. Really... Yeah. So you see when they are arranged in an array like that, ideally you could say, okay, I can, for instance, try to engineer each of them to be providing like a plateau phase front like that. And so something that resemble, let's say, what a pixel of SLM would provide. And then I would have like a large number of them, and somehow I would try to achieve, as you said, reconfigurability as induced by SLM. So it's a bit more difficult here because of the following reason. So when you have them arranged in an array, because heat diffuses, you're going to have some crosstalks, and these crosstalks will happen. So between adjacent pixels, and eventually they will somehow limit, let's say, the accuracy with which you're going to be able to control. So they are a solution we're trying to think about. So to have this collective response. So what I'm trying to say is that in this video I was showing, it is not critical because the pixels are quite separated from each other. But if you start really aiming at pixelizing an image with many of these lenses, then you're going to have to bring them very close from each other. And so you would face this difficulty.
I see.
So we're trying to think about it. And in fact, there's a question then of heat management. So engineering basically, yeah, temperature and the heat at the surface. And so this is not a simple problem. This is an interesting problem.
Sure. But do you think you could achieve better transmissions like with a standard SLM or?
So transmission, I think, so that's important what you asked, because the system I was showing, so everything that is in this paper is actually made of a thin gold layer. So this is a 40 nanometer thin layer. And so this is, let's say, quasi, well, it starts to be opaque because it's in the transition. And eventually here the transmission in the order of 60–65%. Now what we're doing, and this we have a new student working on that at the heart, that is using ITO. And now we reach levels of, let's say, rather 85–90% transmission. So this is becoming, let's say, better.
That's nice. Yeah, for the people in quantum optics, this is very nice because, you know, you want your photon to be transformed, but you don't want to lose it. So it's pretty
completely. Nice. And this is actually critical also for bioimaging. So for instance, for calcium fluorescence imaging, where the photon budget is very tiny as well. So this is exactly the same problematic. Yeah.
Very nice. So more questions, guys? Does anybody want to ask last question? So if not, let's thank our speaker again. Romain, it's really interesting. Thank you very much for
Thank you.
I enjoyed it very much, and I'm sure everybody else
Thank
did.
You so much.
So yeah, I hope next time we can do it in person, so you can.
That would be wonderful. Yeah.
Okay. So
take care, everybody. Thank you.
Bye bye.
Bye. Bye.